Okay, so now we're going to look at two theorems, which essentially are going to show us how we can combine Riemann integrals together. So the first theorem, I'm going to write it in a sort of high-level language. What I'm going to say is that the Riemann integrable space on AB is a vector space over R, and the map T, the map T which takes a Riemann integrable function to the real numbers, defined by T of f equal to the Riemann integral of f, is a linear map. Okay, so it's possible that you haven't seen the words vector space and linear map. But what this theorem says, and you can state this theorem without this language, however, I think it's nice to sort of see it in this sort of algebraic way. What we're going to show is that if I have two functions which are Riemann integrable on some interval, then if I add them or if I multiply them by a scalar, I also get a Riemann integrable function. And the value of these sort of sums and scaled up functions are such that it's the same as if I added the integrals or if I scaled up the integrals. So that's what we're going to show. So first, let f and g be in our Riemann integrable space. So we're going to show that f plus g is in the Riemann integrable space, and we're going to show that the integral of f plus g is equal to the integral of f plus the integral of g. So let epsilon be greater than 0. Let L equal to the integral of f of x dx. And let M be the integral A of g of x dx. Okay. Then there exists delta 1, delta 2 greater than 0, such that P1 less than delta 1, or the mesh of P1 less than delta 1, and the mesh of P2 less than delta 2 implies that the difference between the Riemann sum of f and L is less than epsilon over 2, and the, this is P1, and then the Riemann sum of G minus M is also less than epsilon over 2. Then we can let delta be equal to the minimum of delta 1 and delta 2. So that then if P is less than delta, then P is less than delta 1 and P is less than delta 2, which means that both of these inequalities are satisfied for P. Now P, both inequalities are satisfied for Now, the first thing to note is what happens to our Riemann sum. Sorry, I suck at drawing braces today. This Riemann sum we can just expand I equals 1 to n of f plus g evaluated times delta xi. And then the addition of two functions, right, it's just f of xi plus g of xi, and then we can essentially just break this up. This should be fairly straightforward. But just to illustrate the fact that the Riemann sum of f plus g is in fact equal to, so I'm just going to write the shorthand, this is equal to the Riemann sum of f plus the Riemann sum of g. And of course we're using the same partition here. So thus, if we have p of f plus g, and I'm just going to start sort of not using the evaluation points if the context is clear. So thus, this absolute value, right, p of f plus g is p of f plus p of g, and then we can use the triangle inequality here. Plus p of g minus m, and this is less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay? So that's the first part of the theorem. So now we're going to deal with constant multiples, right? So let's see, be a real number. So the first case, sort of a pesky case, if c is equal to 0, then c times f is equal to 0, and right, we know that the integral of a constant function is just that constant times the length of the interval, which, so this is 0 times b minus a, which is 0. But c times the integral of a to b of f of x dx is c times l, which is 0 times l, which is 0. So that's sort of the first case, showing that the integral of cf is equal to c times the integral of f. Now that we have that case out of the way, we can assume c is not equal to 0, and so there is a delta greater than 0 such that whenever the mesh of our partition is less than delta, the Riemann sum of f minus L is less than epsilon divided by the absolute value of c, right? So this is why we had to break it up into two cases, because if c is 0, then we would be dividing by 0 here. But when c is not 0, the absolute value of c is not 0 as well. And we can just multiply both sides by absolute value of c. Absolute value of c is a positive number, so it keeps the inequality sign, and then we can bring c in here, and we get that c times p of f minus c times L is less than epsilon. And now we just need to show that c of p of f is equal to p of cf. And the proof is pretty straightforward again. We just write it as this, and if I multiply a sum by a constant, I can bring the constant into the sum. So this is c times f at x times delta x, and if you like, I can write this as the function cf evaluated at x delta x. So this is P of CF. And that concludes this theorem. Okay. Now the next theorem, it's not similar, but the proof is going to be similar somewhat. If A is less than or equal to B, less than or equal to C, and F is in the Riemann integrable space on AB, and F is in the Riemann integrable space on BC, then F is in the Riemann integrable space AC. And furthermore, the integral of F on AC is going to be the sum of the integrals of F on AB and on BC. Okay, so what we're going to do is let L be the integral on AB and M be the integral on BC, and let epsilon be greater than 0. Then we have delta 1 and delta 2 greater than 0, such that when the mesh of P1 is less than delta 1 and the mesh of P2 less than delta 2, then we know that the so P1 is a partition on AB, and P2 is a partition of BC. Then we know the Riemann sum of F minus L is less than epsilon over, we're going to say epsilon over 3, and P2 of F, this Riemann sum is taken over BC, minus M is also less than epsilon over 3. So now what we're going to do is, we want to show that F is integrable over AC. So we want P to be a partition of AC. Now P might not be a partition, or might not be a union of partitions of AB and BC, right? But that's an easy case. That's easy to fix. But the first thing we're going to do is we're kind of going to throw in. So you might notice that we have epsilon over 3 and an epsilon over 3. So you might suspect that we need some other term in order to get epsilon. So what we're going to do here is let B be the sup norm of F on AC, right? So first we have to check that this exists, right? We can recall that the sup norm exists if and only if F is bounded on AC. Well, we know F is bounded on AB and F is bounded on BC, and therefore it's bounded on AC, right? If it wasn't, then it would have to be unbounded on one of these intervals, and then it wouldn't be integrable. So F is bounded, and so we can set B equal to the sup norm, and then we are going to let delta be the minimum of delta 1, delta 1, delta 2, and this number might look very funky, epsilon over 9b. And we'll see why we choose this number later on. Right. You can sort of guess that we might be multiplying by 3b in order to get epsilon over 3, right? So that's what's going to happen. So now let P, this is going to be a partition on AC, have mesh less than delta. So simultaneously, P has a mesh less than delta 1 and delta 2 and epsilon over 9b. Okay. Now let P prime be P union the point B, right? So then P prime is a union of partitions on AB and on BC. And the mesh of P prime is still less than delta, right? Because by adding a point, what we're doing is, assuming that it's not already there, which you don't have to do, right? B could be in P a priori, right? But we don't know that. But if you're adding a point into a partition, then you can't be making a bigger subdivision, right? The least you could do is not change any of the subdivisions. But if you are changing a subdivision, then you're cutting it into two smaller pieces. So the mesh can't be getting bigger, right? So in fact, we know that the mesh of P prime is less than or equal to the mesh of P, which is less than delta. Okay. And also we know also the mesh of P1 and the mesh of P2, they're both also less than delta. Because if one of their subdivisions were greater than delta, then we would have a subdivision of P prime being greater than delta. Okay. So now what we're going to do, right? Remember that P is the partition that we chose for AC, right? We need to evaluate the Riemann sum of P, right? So that's what we're going to do. We're going to look at the Riemann sum of F minus the value L plus M, right? Because we're trying to prove that the integral of F is equal to L plus M. And now we're going to use the triangle inequality. We're going to have the Riemann integral of F with respect to our partition P minus the Riemann integral of F with respect to the partition P prime where we've added in the point B, right? And then we're going to have P prime of F minus L plus M, right? So here we've used the triangle inequality to introduce this term, P prime of F, and split it up. And then we're also going to split up this second part. So I'm going to keep this just for shorthand. I'm going to write this P minus P prime. And then we can split this up, right, into P1 and P2. So we're going to have P1 minus L and P2 minus M. Okay. And so since P1 and P2 have meshes less than delta, P1 has a mesh less than delta 1, and P2 has a mesh less than delta 2. So these terms are both less than epsilon over 3, so we need to show that this term is also less than epsilon over 3. Okay, and the way we can do that is essentially by noticing that the difference between the Riemann sum of P, or over P, I guess I should say, the Riemann sum over P and the Riemann sum over P prime, the difference in the Riemann sum so really you can split this up into two cases. You can have the case where B is already an element of P, in which case P prime is just equal to P, and so this term is 0. If you assume that B isn't in our partition, then B is exactly in some interval. So, so the difference in the Riemann sum comes from, there is exactly one interval in P and and 2 in P prime, right? Because in P prime, right, it's P1 union P2, and P1 and P2 are both going to have B in their partition, and so there's going to be 2 intervals containing B. Thus, the difference between the 2 Riemann sums here is going to be at least 1 plus 2, right? So 1 interval plus 2 intervals times the largest possible width of these intervals is delta, right? Because we know that the meshes are less than delta, and the mesh represents how big our intervals are. And then the biggest possible value of f, or at least the absolute value, is going to be b, right? That's what the sup norm means. It's the, how big can the absolute value of f be? And so we know delta is less than epsilon over 9b, so this is 3b times epsilon over 9b, which is epsilon over 3. And so therefore, right, we have epsilon over 3, epsilon over 3, epsilon over 3, so this whole thing is less than epsilon, which shows that this Riemann integral of f over AC is, in fact, the sum of the integrals over AB and over BC. Okay? And so that concludes the theorem. The last thing to sort of say is that we're, what happens in the case where you want to integrate sort of backwards? Like, we know how to integrate from 0 to 1, but what if we wanted to integrate from 1 to 0, right? Because, writing like an interval notation like this, we sort of assume that b is greater than or equal to a, right? But what if we wanted to integrate backwards, in a sense? So we are going to define if b is greater than or equal to a, then we're going to define the integral from b to a of f of x dx to be the negative of the integral from a to b of f of x dx. Okay. And also, this allows us to generalize this theorem that we just proved, right? So notice that in this theorem, B was a point between A and C, and we split up the integrals over, sort of between the point B. But this formula actually holds in general, right? And so one example of this, there are multiple different cases, but I'll just show one of them. If C is between A and B, then we know that the integral from a to b of f from this theorem, right, just an application of the theorem, is the sum of these two integrals, c to b, f of x dx. And then we can apply this definition to reverse the order of integration here. And then we can add on both sides the quantity integral of f from b to c. So we get that this equation holds. And so notice now this is exactly sort of the equation that we just proved, but c is between a and b instead of before, right? C was bigger than a and b, or bigger than or equal to a and b. Also, as a consequence of this definition, right, we have that the integral from a to a is 0. But really, you could have already done this sort of with a partition. Well, the only way you can partition the interval from a to a is just one point, and then if your delta, essentially you would just have to choose delta equal to epsilon, and you would get what you need for this. But right, but essentially this is because we have a to b f of x dx plus the integral from b to a of f of x dx. And since these are negatives, right, they cancel out and you get 0. Okay. So next we are going to just go through some sort of examples of these Riemann integrals, some important examples.